right, everybody. Here are our notes for the slides on force and mass and newtons. Okay, so first, here is the definition of a force. A force is defined as a push or a pull that acts on an object. So, if you shove your little sibling, you are making a force on your little sibling. And we measure this in newtons, named for Sir Isaac Newton. So now we have net forces. So this is the combination of two different forces, like our pups here having a tug of war. That is a net force. So now there are two kinds of net force. Are they balanced or are they unbalanced? So if two forces are balanced, nothing will move. So if those two puppies in the last slide were perfectly evenly matched, that's balanced. Neither puppy is going to win the tug toy there. If one of the puppies is stronger, now we're talking about forces that are unbalanced and the object, the pull toy, will move. Inertia is known as an object's resistance to a change in motion. So an object at rest tends to stay at rest unless acted upon by an outside force. So that means that cat is not going to get up until something makes it get up. And for all of our cat people, we know how stubborn they can be. Cats, I think, have more inertia than your average pet species. All right, now we got to think about inertia and mass. I love this fat cat. It's just so round and gloriously like a soccer ball. It's excellent. So the more mass an object has, the more force it takes to make it overcome inertia. So that kind of makes sense, right? The bigger it is, the harder you're going to have to shove it to get it to move. So now, here we are with our buddy Newton and his laws of force. So please be assured that I will never ask you which is the first law or the second law or whatever. I'm more concerned that you know the content in them than which number is which. Okay, but law number 1. An object at rest will... All right, so there's my big flub for this one. Okay, so an object at rest will stay at rest or will keep moving at a constant velocity unless acted upon by an outside force. So if it's at rest, it's not going to move unless you push it in some way. Or if it's in motion, it will stay in motion unless there is an outside force there. So this is that thing about if you throw a baseball in space, it will go on forever because there's nothing to stop it. There's no air, there's nothing there, no wind to make it stop. Okay, now we have Newton's second law. The acceleration of an object depends on the amount of mass it has. So this is often represented by this equation here, F equals ma. Force equals mass times acceleration. So this is kind of putting all those things together. If you're going to push a shopping cart, you don't need as much force to make a shopping cart accelerate as you would need if you were trying to make a refrigerator accelerate. Refrigerator has more mass, it's much bigger. You have to shove it a whole lot harder to get it to move than you would a shopping cart. And then there's Newton's third law. For every action, there is an equal and opposite reaction. So these two people in their ice skates here, if they push at each other, they will push forward, but they will go backwards. That's the opposite reaction. The push forward is one, and then the push backwards, because they're sliding, is the opposite. Another way to think about this is a soccer ball. You're kicking a soccer ball. Soccer ball goes forward, but you can feel that push back in your foot. But you have more mass. Therefore, you make an unbalanced force on that soccer ball, and you make it move rather than it making you move. All right, so now we've got to talk about momentum. So this is the quantity of motion that an object has. And this same as before, has to do with mass. It's all about how big and heavy things are. What do you have to do to get them to move? And then in here, we got to have a bit about the speed too. That's the velocity. So the greater the mass, the greater the momentum. But if the velocity is 0, then there's no momentum. So this is my analogy that I used earlier, where the difference in if a football player ran into you as opposed to a little toddler. A football player is going to hit you a whole lot harder than a toddler will. But if the velocity is 0, nobody's running anywhere, well, now we have no momentum. All right, everybody. I'm going to upload this to Google Classroom, and I hope this helps you get through those questions in that reading. Everybody have a great day. Stay safe out there.